Hello everyone. This week's lecture will cover Module 2 and is divided into two parts. Here in Part 1, we will discuss chemical bonds, the octet rule, and naming of ionic compounds. Atoms do not exist in isolation from other atoms. Because they are everywhere, they will encounter other atoms. For some atoms, this meeting results in the formation of a bigger particle, a molecule. But for other atoms, no such formation takes place. They just ignore each other, or they move away from each other. Remember that all atoms carry charges, either positive or negative. The surface of atoms contains negatively charged electrons. The nucleus contains positively charged protons. The charges that atoms carry are responsible for creating electrostatic interactions among them. These interactions can be either attractive or repulsive. Electrostatic attractions or repulsions between atoms do not have the same strength. They can be either strong or weak. The results of these electrostatic interactions determine whether two or more atoms can bond to form molecules. Electrostatic attractions lead to the formation of chemical bonds, and the type of atom determines what type of bond it can form with other atoms. In Module 1, we learned that when an atom gains or loses an electron, it becomes an ion. This ion can have either a positive or a negative charge. When a positively charged ion meets a negatively charged ion, they form an ionic bond. Ionic bonds create ionic compounds. We learned in Module 1 that when a metal bonds with a non-metal, they form an ionic compound. Ionic bonds form because one of the ions donates its outermost electron to the other ion that needs it. This is how table salt forms. An atom of sodium donates its outermost electron to an atom of chlorine, thus creating the molecule sodium chloride. On the other hand, covalent bonds form when two atoms share their outermost electron with each other. We learned in Module 1 that covalent compounds form between nonmetals or between nonmetals and metalloids. An example of covalent bonding is methane, or CH4. In methane, carbon shares its four outermost electrons with four atoms of hydrogen. Not all atoms that meet will form molecules. Some atoms will not react with other atoms, whereas other atoms will be highly attractive to other atoms. What governs this property? Atoms follow a set pattern of chemical bonding that is determined by their valence electrons. What are valence electrons? Recall the different atomic models you learned about in Module 1. One of the earlier models was the Bohr model, proposed by Danish scientist Niels Bohr. Although this model is not the accepted one today, it is very useful in illustrating how and why molecules form between certain atoms only. This model shows the atom having a central nucleus containing protons and neutrons. The electrons orbit this nucleus in electron shells or energy levels. Energy levels are designated by a number and the symbol N. The 1N shell represents the atom's first energy level. The 1N shell can hold a maximum of 2 electrons. The 2N shell can hold up to 8 electrons, and the 3N shell can hold up to 18. The outermost shell of an atom is called the valence shell, and the electrons in this shell are referred to as valence electrons. The valence shell can contain up to 8 electrons only. Valence electrons are the ones that form chemical bonds. Thus, they largely determine an element's chemical properties and reactivity. Recall that in a neutral atom, the number of protons equals the number of electrons, and the number of protons is the element's atomic number. Electrons fill each energy level from the lowest to the highest. So, we can determine how many electrons a certain element has in each of its energy levels.
We can then know how many valence electrons the element has. If we distribute an element's electrons among the atom's electron shells, we will not always have 8 electrons in the valence shell. Let's take the case of nitrogen, potassium, and bromine. The atomic number of nitrogen is 7. This means it has 7 electrons. We can distribute these 7 electrons in the energy levels of nitrogen. The lowest energy shell can hold up to 2 electrons only. So, the remaining 5 electrons can be distributed in the valence shell of nitrogen. Potassium has an atomic number of 19, so it has 19 electrons. If we distribute these 19 electrons in the energy levels of potassium, we will have only 1 electron in the valence shell. Bromine has an atomic number of 35. It has 35 electrons. If we distribute these 35 electrons in each of the energy levels of bromine, we will have only 7 electrons in the valence shell.
Why is having 8 valence electrons important for an atom? An atom that has 8 electrons in its outermost shell is stable and unreactive. An atom will always seek to be stable. The octet rule best describes this condition for all atoms. It states that a stable arrangement is attended when an atom is surrounded by 8 electrons. This octet can be made up by own electrons and some electrons which are shared. Thus, an atom continues to form bonds until an octet of electrons is made. An atom can form as many bonds with other atoms as there are electrons in its valence shell. So an atom with 4 valence electrons can form up to 4 bonds with other atoms. Noble gases are considered the least reactive, most stable elements because they already have 8 electrons in their valence shell. Although helium only has 2 electrons in its valence shell, this constitutes a pair. Hence, it is stable. To achieve the same stability, other elements will lose or gain valence electrons either by donating them to form ionic bonds or by sharing them to form covalent bonds. In both cases, an element will form a chemical bond with another element by pairing up their electrons. How many electrons do elements have in their valence shell? We can look up the periodic table to see in which group an element belongs. The number of valence electrons increases from left to right. This means group 1 elements have 1 valence electron. Group 2 elements have 2 valence electrons. Let's skip groups 3 to 12 first and jump to group 13. Group 13 elements have 3 valence electrons. Group 14 elements have 4 valence electrons. Group 15 has 5. Group 16 have 6 and group 17 have 7 valence electrons. The elements in groups 3 to 12 take on many forms, so their valence electrons tend to vary. The valence electrons of each element will tell us how many more electrons they need to complete the octet rule. Those in group 17 have 1 less valence electron, so they need 1 more to be stable. Nitrogen, which is in group 15, has 5 valence electrons. This means it can accept up to 3 electrons from other elements to complete its octet requirement. On the other side of the periodic table, lithium has 1 valence electron, and magnesium has 2 valence electrons.
To complete their octet requirement, Group 1 and Group 2 elements do not take in 7 or 6 valence electrons respectively. Rather, they donate their electrons to elements that need just 1 or 2 more to make 8. They do this because it requires less energy to lose electrons than to gain 6 or 7 of them. Let's take the case of sodium chloride. To form an ionic compound, sodium donates its lone valence electron to chlorine, which needs just 1 more to complete its octet requirement. Why would sodium lose its electron? Because it is more energy efficient for sodium to lose just 1 valence electron than to take in 7. This is true for the other elements in groups 1 and 2 of the periodic table. Let's take the case of magnesium oxide. Magnesium has 2 valence electrons. Oxygen has 6. It is more energy efficient for magnesium to lose 2 electrons than to accept 6. It is more energy efficient for oxygen to receive 2 electrons than to give away 6. So, magnesium can donate its 2 electrons to oxygen to form magnesium oxide. In this way, oxygen now has 8 valence electrons. Elements in groups 13 to 17 can form molecules amongst themselves. Remember that nonmetals can form covalent compounds with other nonmetals. Let's take the case of H2O or water, CH4, methane, and CCl4 or carbon tetrachloride. Oxygen has 6 valence electrons. It needs just 2 more to complete the octet. Hydrogen has 1 valence electron that it can share with oxygen, thus forming the compound H2O. Carbon has 4 valence electrons. So, it can share 4 electrons with other atoms to complete its 8 electron requirement. In this case, carbon shares its electron with 4 atoms of hydrogen to form methane or CH4. Carbon can also share its 4 valence electrons with other elements that need 1 more electron. For example, chlorine. 4 atoms of chlorine can bond with 1 atom of carbon to form carbon tetrachloride. Not all atoms that form bonds follow the octet rule. Hydrogen only has 1 electron. It follows what's called the duet rule. Hydrogen only needs to pair its lone valence electron to be stable. Other atoms need either fewer or more than 8 valence electrons to achieve stability. Examples are boron, sulfur, and phosphorus. Boron only has 3 valence electrons. It can form 3 bonds with other atoms. Fluorine has 7 valence electrons. It needs 1 more to complete its octet. So, the 3 atoms of fluorine can pair with each of the 3 valence electrons of boron to form a compound. This compound is boron trifluoride. Fluorine now has an octet for all 3 atoms. Boron has less than an octet, with 6 valence electrons. But it is stable because all its valence electrons are paired. Some atoms can go beyond 8 valence electrons to achieve stability. Phosphorus has 5 valence electrons. It can accept 3 electrons to form phosphorus trichloride
or it can share its 5 valence electrons to form phosphorus pentabromide. Sulfur has 6 valence electrons. It can accept 2 more electrons to complete its octet by forming sulfur dioxide, or it can share each of its 6 valence electrons to form sulfur hexafluoride. Note, however, that this ability of sulfur does not apply to all elements in the same group. Oxygen also has 6 valence electrons, but it can share only 2 of its valence electrons, not 6. What is common about these exceptions is that their valence electrons only need to be paired with other valence electrons to be stable. We learned in Module 1 about ions. Ions are formed when an atom gains or loses an electron. An ion that loses an electron becomes positively charged because it now has more protons than electrons. On the other hand, an ion that gains an electron becomes negatively charged because it has more electrons than protons. A positively charged ion is called a cation. A negatively charged ion is called an anion. An atom written with no charge is considered a neutral atom. An atom with either a positive or negative charge is an ion of that atom. Examples of cations are the sodium ion, magnesium ion, and aluminum ion. Examples of anions are the chloride ion, the oxide ion, and the nitride ion. We learned earlier that the number of valence electrons can be determined by looking at the elements grouped in the periodic table. We can also determine how many electrons an element can lose or gain by looking at their group number. There are 3 important points that you have to remember when talking about ionic charges. First, group 1 elements tend to lose 1 electron. Group 2 elements tend to lose 2 electrons. Group 17 elements tend to gain 1 electron. Group 16 elements tend to gain 2 electrons. Group 15 elements tend to gain 3 electrons. Second, the elements that form cations are metals, and the elements that form anions are nonmetals. This is one of the unique chemical properties that distinguish metals from nonmetals. Third, most of the atoms that form ions with a specific charge. For example, when sodium forms an ion, it always has a +1 charge because sodium only has 1 valence electron. On the other hand, when chlorine ions form, they always have a -1 charge because chlorine needs only 1 electron to complete its octet. But there are some exceptions to this point. Some metal elements can form more than 1 possible charge. For example, iron can have a charge of either 2 plus or 3 plus. Lead can have a charge of either 2 plus or 4 plus. As you become familiar with these monatomic ions, remembering what charges they characteristically have will be easier. Recall our lesson on naming covalent compounds in Module 1. Naming ionic compounds is just as simple, but not quite the same. Before we get to that, let's first distinguish between a neutral atom and its ionic form. Neutral atoms are named by the name of the element. Cations are named by adding the word ion to the element's name. So, calcium is the name of the neutral atom. Rubidium is the name of the neutral atom. To refer to the ion form, we simply add the word ion to the element's name. So calcium ion refers to the charged atom, and rubidium ion refers to the charged atom. When it comes to anions, we use the stem of the element's name, add the suffix IDE, then add the word ion. So, fluorine is the name of the neutral atom. Oxygen is the name of the neutral atom. To name the anion, we take the stem of the element's name, add IDE, then add the word ion. This gives us fluoride ion. For oxygen, the stem is ox. We add IDE and ion. This gives us oxide ion. Ions made of only one atom are called monatomic ions. Ions made of two or more atoms are called polyatomic ions. The molecular formula that we studied in Module 1 is used to represent covalent compounds. We use the Ionic formula to represent ionic compounds. When writing and naming ionic compounds, we put the cation first, the anion second. Let's take the case of lithium chloride and magnesium iodide. When lithium donates its electron to chlorine, it forms lithium chloride. We write lithium first and then chloride second. For magnesium iodide, we write magnesium first and then the iodide ion next. When writing and naming ionic compounds, it is important to note that the total charge of the ions in the compound must be equal to 0. Let's take the case of magnesium iodide. Magnesium has a 2+ charge. The iodide ion only has a -1 charge. In order for magnesium iodide to have a 0 charge, we need 2 atoms of the negatively charged iodide ion. So, the formula for magnesium iodide becomes magnesium iodide 2. In this way, the total charge of this molecule is 0. The first rule in naming ionic compounds is to simply combine the name of the cation and anion without the word ion. The cation is named as is. Earlier, we learned how to name anions. We take the stem of the element's name, then add the suffix IDE. Then, we combine the cation and anion names. So, for our example, Ki, the name of the cation is potassium. How do we name the anion? The stem of iodine is iode. We add IDE. So this is iodide. Combining the cation and the anion names gives us potassium iodide. When naming covalent compounds, we use number prefixes such as di for 2, tri for 3, and tetra for 4. We do not use these prefixes when naming ionic compounds. We just name them as we would if there was just one atom. So, in our example, we have magnesium chloride and aluminum trifluoride. The name of the cation is magnesium, and the name of the anion is
dichloride. Although there are 2 atoms of the chloride ion, we do not name it as dichloride in ionic compounds. So in the second example, the name of the cation is aluminum, and the name of the anion is fluoride. Once again, we do not use the prefix tri when naming ionic compounds. Some elements, especially those belonging to transition metals, can have ions with more than one possible charge. For example, iron, cobalt, and nickel come in 2 forms, a 2+ charge or a 3+ charge. When naming these ions, we need to indicate which form is part of the compound. We do this by writing the charge using Roman numerals after the name of the cation. So for our example, we have 3 forms of the compound with iron and oxygen. To name the first compound, this one has iron with a 2+ charge. We already know that oxygen has a 2- charge. We name this compound as iron 2 oxide. This compound has iron that comes with a 3+ charge. So we write iron 3 oxide. This compound has both the 2+ and the 3+ forms of iron. So when this happens, we write both of the forms in the name of the compound. Note that many references still refer to this compound as ferrous oxide. This compound is referred to as ferric oxide, and this one is ferric oxide. Both of these forms are correct, but the one with the name iron is newer, and it is the more accepted name for this compound. So far, we have tackled ionic compounds that form between monatomic ions. Ions do not just exist as individual ions or as monatomic ions. Some ions are polyatomic. That means they are composed of 2 or more atoms of different elements, and they have either a positive or negative overall charge. Many of the polyatomic ions in this table are important in both organic chemistry and agriculture. It is best to become familiar with these ions. When naming ionic compounds with polyatomic ions, we simply combine the name of the cation with the name of the polyatomic ion. Here we have the polyatomic ion nitrate and sulfate bonded to potassium and magnesium respectively. So the name of this compound is potassium nitrate, and the name of this compound is magnesium sulfate. Some ionic compounds are combinations of polyatomic ions. The naming rules are the same as before: cation first, anion second. In our example here, we have 2 polyatomic ions, ammonium and nitrate. Here we have ammonium and phosphate. So to name this, we write the name of the cation first and the anion second. So we have ammonium nitrate and ammonium phosphate.
This ends part 1 of Module 2. Please proceed to part 2 in the next video. Thank you for listening.